Yes, good afternoon, students. Yes, okay, fine. Yes, we will continue now after this. So, yesterday I have finished till extraction of iron. We shall proceed now. So, this part I have explained, so I will not go for that. We will move on with the next topic. Today's topic, what we are having. See, after the extraction is over, I have told you that down you can see that they are in two layers. You could see those two layers, no? So one is for the slag part, slag which is light in weight. So one is for that slag part, you can see here. And one more we are having, that is for iron. Molten iron being heavier, they will settle down at the bottom and they are collected on this side, collected from one end, and you can see the slag being a little light in weight is collected from the another side. Okay, now after this, see, these ions are categorized into different. We call them with different names depending on how much of impurities are present in them. So now the first category, what you are going to learn, it is also called as pig iron. This iron is there, no? It's called as pig iron. That's because of the impurities present over here. The iron which is obtained from the blast furnace, they contain, you see here how much they have given. It is around 4% of carbon. 4% of carbon is present as impurities here. And along with that, there can be some other compound also. Like it can have sulfur, phosphorus, silicon, manganese. Okay, these can also be present along with this. Okay, and it can be shaped into different shapes can be given for these pig ions. Then next one, the second category of iron what you are having, that is called as cast iron. Cast iron is different from that only in these. You see what are the different things we are using here. It consists of scrap iron, and then they are making use of coke and slightly lower compound, like the carbon content. The content which is there of carbon is little less here. Okay, about 3%. There you saw in pig iron it is almost 4%. So this is extremely hard and they are brittle also. These are hard and brittle. So scrap, now what is this scrap iron? Scrap iron is the used ones are there, no? The waste ones which is again recycled. Now we will have these iron waste. Either it can be in the form of vessels or it may be any iron materials. So that is being recycled again during the process along with this iron which is obtained from the blast furnace. Along with that, this is heated. So that is scrap iron. If you, I don't know how many of you have read about this. This time the Olympic medals were prepared from the scrap materials. No, scraps are those unwanted, the waste materials. So you know, so many electronic items contains metals. Have you read about that? I have just displayed that picture so that you're aware. And this is the whole metallurgy process only. If you want to extract the metal again from the electronic items, you need to know what is the process has to be used. So see here, if you have read about this, almost 5,000 metals which are prepared, that is extracted from the electronic items this time. Okay, so they have collected across the Japan, they have collected these and see how much amount of gold, silver and bronze they were able to extract from these donated devices. See, almost 32 kg of gold. Can you imagine how much it is? It is throughout the Japan, but then still this much amount of gold they could get back from the electronic items. Otherwise, it will be a waste, you know. Directly it will go into the soil. So see this much 32 kg of gold has been extracted around see 3,500 kg. See, it's so huge it is. This much amount of silver has been extracted and around 2,200 kg of bronze has been extracted from these many tons of electronic devices, donated devices. So this time the medal, that was one a good part no, of Japan, that they have used this and it was not a waste. So even here when we are doing the casting of these irons, along with this, the one which I used in pans, the one you have seen the water pipes, the huge pipes, they are iron only. Okay, so those are made up of scrap iron, the recycled, sorry. Along with that, around 3% of carbon content will be there. Okay, so they are quite hard and they are quite brittle. Then we have another category of iron, that is wrought iron. Wrought iron is the purest form. Purest form, almost, if I have to tell you the iron content in this, almost 99.4%, roughly I'm giving you this. Okay, so around 99.4% of iron content is there in this, and very less amount of, you will find the carbon. Maybe around 0.1% of carbon will be there, 0.1%, and other will be the slag part. Okay, so you can see here the 99% is iron itself in that, remaining are the other impurities. So wrought iron is the purest form. They ask you what is wrought iron, you should remember it is the purest form and most malleable also, because see, soft, the pure form of ions are quite soft. If you want to make them hard, you need to add this carbon content. So carbon will come. You have studied, no, transition metals. When I was explaining transition metals, I have told you about alloy formation. So when you take iron and then you add carbon into that, this carbon will go and sit, no, in between, and then they will make the material little harder. Okay, so that's been prepared like that. How it is prepared also they have just told here. So limestone is added as a flux and the other materials are oxidized and passed into the slag. So most of the things are removed out through this method. Okay, so yeah, this much is enough if you know. We'll go on with the next extraction. This was just an example, wrought iron gate. Okay, quite malleable they are, so they are used, the uses of that. Okay, moving on with the next extraction of copper. Copper is extracted from copper pyrite. Copper pyrite is the ore. I'll give you the formula. This is the copper pyrite ore, which I have displaced here. So copper pyrite or copper pyrite, you can write. It is having composition of Cu, FeS2. It is having copper, iron and sulfide. It's a sulfide ore containing iron and copper along with that. So you know, if it is a sulfide ore, what are the methods you are supposed to apply? First thing, if you want to do the concentration, what you are supposed to do, now you should reply and tell me. If it's a sulfide ore and if you want to concentrate this, how is the concentration done? Concentration of the ore. What is the method? Out of those 4 methods which I have taught you, that is hydraulic washing we had, magnetic separation we had, then you had froth flotation. Correct, no? Among all that method, which one will you apply for this copper? You tell me now, reply. For concentration, it's a sulfide ore, no students. So if it is a sulfide ore, how the removal of unwanted impurities will be done by froth flotation. Yes, very good, correct. So it will be done through froth flotation. So that picture also I have displayed here. So you can see on this side, sulfide ores are taken. You are supposed to add the collector, you add the stabilizer, agitate the mixture. Okay, so once you agitate the mixture, you can see that the lightweight ore along with the collector and the stabilizer will form the froth, and that has been skimmed off. You can see, here continuously they are agitating that mixture. On the other side, I hope it is visible. Yes, so continuously it has been agitated. So when you agitate that, it will form a froth and that has been skimmed off. After this, now again you are just removing the unwanted impurities. Now after this, you are supposed to roast them. So here the next process you are doing is roasting, because again it is in sulfide form itself. No, we have just removed the unwanted impurities associated with them. So you can see a furnace here. So they put them into the furnace and then they heat them at very high temperature and oxidize these impurities. Okay, so the sulfide ore which is present here will get oxidized. That equation I'll tell you later. So once that is over, then everything is put together. The other side, you see towards the right side, you can see here everything along with your ore, flux, everything is added together. From this side, hot air is being passed and you are heating them in the reverberatory furnace at very high temperature. So you heat them, then this finally the copper which is present over there, They will be in the copper sulfide form. Okay, copper sulfide will get oxidized. They will form copper oxide. After that, even your sulfide, iron sulfide also will get oxidized, from iron oxide, and then undergo self reduction. They undergo self reduction. They have that no tendency to undergo reduction by themselves, and then finally copper has been obtained. That equation part I'll tell you. And whatever impurities are present, that will be removed in the form of slag. So let me just give you the equation how it has been done here. So finally you are getting that copper. You can see that coppers are collected here. Copper has been collected in all of these molds you can see here. So it will be at very high temperature. You can see how it will be. Okay, and then see, after the cooling has been done, this is how it will look. And copper, if you have a closure look of this, this is the final closure picture of that. You can see it looks like a blisters, as if blisters are there on top of that. Okay, so it is because of that look only, they are even called as blister copper. These are called as blister copper. Okay, these are called as blister copper. That's because of the blisters which is formed. That blisters are formed because of evolution of sulfur dioxide gas. That I'll explain to you. Okay, so this was just a gist to give you what is happening. Now let's go with the equation. So initially, when you are taking copper pyrite, let me go with the equation. Copper pyrite is FeCuFeS2. Plus, you will be roasting it. This I'm talking about the roasting method now. Okay. Where it is very important, I'll tell you, like you are supposed to study which part of it, but I'll just mention about everything first. When you are doing the roasting, you are taking this whole copper pyrite and you are heating them after the froth flotation is over. You heat them in that furnace which I told you. So after like the roasting process, this would get converted to, see, copper will combine with the sulfide and come out as copper. They break down here. Decomposition happens and copper forms copper sulfide and iron gives you iron sulfide. Plus the sulfur dioxide gas is evolved. We are doing the roasting process. So sulfur dioxide goes out. So initially this happens. First step I am talking about, when you are just heating them. After that, this copper sulfide which is present combines with again plenty of oxygen and form copper oxide. They are in +1 form here. You can see that. Cu plus form it is. So Cu plus form only you take. So this oxide is formed plus sulfur dioxide is obtained. Again the iron sulfide which is present, FeS, that also gets oxidized to give you FeO. FeO plus sulfur dioxide. Okay, I have not balanced this equation. You can balance it. If you balance, you will get here 2 copper. Okay, rest everything is fine here. This, if you want, you can remember it is 22, 23 and 22. Okay, these numbers, if you want to remember, you can balance it. It is not difficult. So I'm just giving you the number right now. Okay, so it will be 23 and 22 when you balance. Even this will be 23 and 22 if you balance. Okay, it will be similar. After this, you are supposed to heat them again because now they are in their oxide form. This is the roasting method I told you. After the roasting is over, then they are again taken, students. These are again taken into that furnace, this furnace. I'll go back here. See, it is taken into this furnace. Roasting is done here. So when you do the roasting here, they will be in their oxide form, which I gave you just now. Copper oxide I gave you and iron oxide I've given you. So they will be in this form. From here, you are supposed to get them into this smelting process. Okay, smelting is heating at very high temperature. So when you heat them at higher temperature, see the next thing what happens. After this is over, after they have got converted into this form, the copper, for us important is copper. So forget about the iron for time being now. So take copper which is formed here, copper oxide it is. This copper oxide, see, complete oxidation may not happen. So there will be a certain amount of copper sulfide still remaining. 100% it won't get converted. So copper oxide, some will get converted and some will be still there. So that itself will act as a reducing agent. Okay, so I said it undergoes self-reduction. So Cu2O combines with the remaining Cu2s and get converted to copper and sulfur dioxide is formed here, SO2. Okay, so if you balance this will be 2 here because 2 oxygen, then you get total 6. So it's balanced. Okay. So this is the equation for copper. First you remember this one, what is happening here. After roasting, what happens? They are in this form. And then after that, immediately you can write this. Now let's speak about that iron which is getting converted to FeO. No, what has to be done with that? That has to be removed. No, that's the impurity for us now, because we are extracting the copper. So iron present over here will act as impurities. Anything other than that metal will be impurity for us. So this has to be removed now. So what we do with that is this iron oxide that I'm writing it down here, FeO, is made to combine with the sand. Okay, this will combine with the sand now and form FeSiO3. Slag will be formed. So you don't need a separate flux over there in a blast furnace for iron extraction. I've told you you are supposed to use a separate flux there. Okay, that is limestone is used, where limestone gets oxidized and then that oxidized compound reacts with the silicate. No, here you see iron oxide will act as, it's a metal oxide. No, metal oxide and silicon dioxide is a non-metallic oxide combined together to give you this salt, which is iron. Sorry, iron silicates are formed, which will be your slag part. So these are the equation now here. You don't have much here, only basics. And if you remember in 10th standard also you had this same thing you had, but you had as copper sulfide, this equation you had. And after that, the second one which I've ticked, that also you had. These two you had in your high school. You have learned this. The only thing, little difference over here is we are taking copper pyrite. Copper pyrite gives you iron sulfide and copper sulfide. So two things are present. So when you roast them, you are getting copper oxide and sulfur dioxide. The iron sulfide present also gets oxidized to give you iron oxide and sulfur dioxide. First, to deal with the copper. This copper oxide which is formed further reacts with their own compound. So I said 100% conversion may not take place. So this copper oxide itself will act as a reducing agent, copper sulfide, and react with one another. They react with one another, giving copper and sulfur dioxide gas. Now deal with this. Yes, no problem, no problem. That's okay. Yeah, so now this iron oxide combines with the sand, the silicates. Okay, so it combines with the sand, that is silicate, to give you the slag. Okay, so write it down, students. Write this down. I'm drawing a line here because similar kind of reactions it is. First one is where you are taking the whole compound and then they are broken down into sulfide. Second, both are roasted here. And the last part is, one is for the copper formation, the last one is for slag formation. So this sulfur dioxide which is formed here, that will interfere with the, see it's like how you have this carbon dioxide when they get evolved. During the cake formation, it creates a hole there. Okay, now these sulfur dioxide which is formed over here creates a blisters like this, because metals are little heavy, you know. So they interfere there in between and they create this blisters. Okay, so it is called as blister copper. And there's a name given for this copper sulfide and iron sulfide together is called as copper mate. So they can ask you this, what is copper mate? So you should know copper sulfide and iron sulfide together is called as copper mate. Yes, did you all finish writing? Yes, no? Okay, very good. Fine. I'll proceed now. Next we are having is the refining process. So I'm directly going for that refining part. There is thermodynamic part of this, why carbon, coke and all that is used. Okay, that part I'll be doing at the end. So we will start with the refining. Once you have extracted the metal, it may not be 100% pure, so you will have to purify that. You have seen, no, in the iron case also there are certain impurities, in copper also there will be so many impurities, so you will have to purify it. So if you want around 100%, any purity cannot be attained, you know that, because technical errors will be there, mechanical errors are there, okay, impurities will fall down during the extraction process, so anything can happen. 100% purity cannot be attained, but at least 99% purity can be attained over here. Okay, so refining is that method where you are trying to purify the metal. Whatever contaminants are present, whatever impurities are present, you are trying to remove it and try to make as much as pure. Okay, you are trying to convert that in the pure metal form. Okay, that process is called as refining. So you are going to study different refining process. Where it is very important, I'll be stressing and I'll put a star mark. Okay, so first we are having distillation. Distillation is one method. Distillation you have learned for liquids. Two liquids can be separated through distillation, no? The one with low melting and the one with high melting. Similar method you can apply for metals also. Okay, so you can apply for low melting, the one which can boil out very easily, no? So low boiling melting, the low boiling metals like zinc and mercury. Mercury anyways exist in the liquid state. Okay, but zinc can also be melted very easily, so these can be separated out through distillation process. Okay, so see how it has been done. This is mercury distillation tank it is. So here they will add, in this the distillation tank, they will add that metal, and the one who is having very low boiling point, they will boil out first. It is same like the way two liquids will come out, no, through distillation process. If you have two liquids there, the one who needs less temperature, the one who is having less boiling point will evaporate first. Correct. No, the one which is having less, I'll just write, the one which has less boiling point, that will come out first. That comes out first. And the one who is having more boiling point, that will stay down. And then if you are having three such one, you can remove that later. Okay. So similarly here, two metals can also be separated like that. And then you have to remove that metals which are in the no liquid state. Allow them to cool down. You will get them in the condensed form. So that is about distillation process. Second one is liquefaction. As the name goes, again you are converting them into a liquid now. Liquefaction is where you are converting again them into a liquid. So it is again applied for the one who is having low melting point. So the metal which is having low melting point, like example here for tin can be applied with this method. So you are, see the arrangement you see here, how the arrangement is. A slope kind of a arrangement you can see, and from this side the impure metal is being fed. From this side they are putting the impure metal. So there is a slope here. So when you put this impure metal, these will start, and this side is the heating done. Okay, down you see, down we are having that heating, continuously heating has been done. So when you heat them at higher temperature, this metal will start melting. Okay, and the impurities will not melt, the impurities will stay here itself. Okay, the impurity stays on the slope, and this metal will start flowing down. Okay, so they flow down and they are collected here down. You see in this vessel they are collected continuously. Okay, what I feel is here there will be some no like there will, it won't be a smooth one. There will be some hindrance for them to stop. So those impurities will settle down here in between. Okay, and the metal, since you are heating that metal continuously, it's in the liquid state, they will melt and fall down. So like that you can separate this. Liquefaction is done for the one which is having low melting point. Next we are having, this is very important, okay. This method is very important, electrolytic refining. As you can see with the name only, it indicates that you are going to pass electricity. So electricity is being passed, and one metal which is impure, the impure metal is taken as anode. Okay, we take them as anode, and the pure metal, a small strip of pure metal you can take, that will be taken as a cathode. Okay, so that is taken as cathode with a suitable electrolytic solution, because when you do electrolysis, yesterday also I told you, for that aluminium extraction, you need an electrolyte through which these ions will start flowing towards their respective electrode. So solution is required here, so same kind of electrolytic solution will be taken. So what reaction happens here? The reaction at anode taking place, see this is overall reaction here. At anode, you know, oxidation happens, and ox I have told you, anode oxidation takes place, and at cathode, reduction is taking place. So at anode, where you have taken the impure one, they should lose themselves. It should go out actually, because you are taking the impure one there only so that they undergo oxidation. So impure is taken as anode, and that metal loses, that depending on their valency they will lose electrons. So generally we are writing as N plus, N electrons are lost. That N electrons lost will come towards the cathode side, will be taken by that ions which are there from the solution. They will come and take that electron and get converted to metal, get deposited there at cathode. Okay, so this will be deposited there at the cathode. So let's see the schematic diagram how it is. This is how it will be. Okay, if you are representing this, on one side we have taken the pure one, and the another side it is impure one. Okay, this side you see impure one is taken. Impure one is maintained as anode, and the pure one is taken as cathode. Everything is taken in a copper sulfate. Since you are talking about copper here, you should have the same ion. Otherwise, there will be mixing. Okay, you will have combination of two metals then. So then it is a problem. Okay, so due to that, you avoid that and take the same metal. If you want 100% pure, okay, 99% pure metal, if you want, you are supposed to take same electrolytic solution. The same ion should be present in that solution. So anode, oxidation will happen. On this side, oxidation takes place. So when the oxidation happens, these copper, which is in the form of rod here, they will start losing, no? They will lose their electron. So now imagine here I am having copper. These are copper metal here. Cu I am writing. Okay, so these copper will lose 2 electron and go into the solution, correct? So 2 electrons will be lost from here, and they will go into the solution. So those Cu2 plus ions, from here these 2 electrons will start moving from the battery and it will come here, 2 electrons. So then you are getting that negative charge because of this. This Cu2 plus ion will start moving from the electrolytic solution and get deposited here. So with the passage of time, you can understand what will happen to the anode side, and you can imagine what would happen towards the cathode side. At the cathode side, as the time passes by, it will become thicker and thicker, and the anode side, since they are losing it, the ions are going into the solution continuously, it will become smaller and smaller. Okay, so this again I have shown it here. You can see, students, copper from this side, okay, from this side, that Cu will go into the solution as Cu2 plus, and those Cu2 plus is going and getting deposited. So with the passage of time, you can see that this side of the cathode is becoming heavier, okay, heavier in mass, and the anode side will become smaller in mass, and whatever impurities are there, that impurities will settle down as anode mud. Okay, so refining through electrolytic method is found to be, okay, the best method, because almost 99% purity can be obtained through this. Now, how will you write the equation? You should know how to write the equation, no? How will be that equation for copper at anode and cathode? Here itself I'll write at anode side where oxidation is happening. Anode side where oxidation is happening. So anode, you are having that copper. So Cu is there. Cu is going into Cu2 plus form, plus 2 electrons they have lost, oxidation, so 2 electrons are lost. And then come to the cathode side. At the cathode, reduction is taking place. So cathode, this is Cu2 plus ion is going there, receiving 2 electrons. So reduction means gain of electrons. So Cu2 plus taking 2 electrons, getting converted to Cu. Okay, then going and getting deposited on the cathode side. So simple equation, same equation it is, but reverse them and write. For oxidation, you put that electron and ions on this side towards the right side. Same thing, that right to left you have to write for reduction. This is an important, this can be asked. You can expect the equation to be asked in the exam. Okay, if you are seeing in the industrial how it has been done, industrial refining, you can see here, this is how they do it. They take sheets of copper, impure and pure, impure, pure, alternate they will take, and dip them into that solution, and then the process has been carried out. Okay, yes. So this I have explained already, this I have told to you. I believe this is clear. So many metals can be purified like this. Did you all understand, students? Just reply and tell me. Was this understood? Yes, no? Okay, good. Yeah, so see which are the metals which can be purified like this. Antimony, selenium, tellurium, silver, gold, platinum, zinc. All these can be refined in this method. Okay, this way you can do the refining. So equations you all remember. I'll go back. This is the equation. Equation you will have to study. And what is taken where? At the cathode side, you are taking the pure metal. Anode side, you are taking impure. That's it. I'll go back for the next one. We'll go to the next process. Next process over here is zone refining. Okay, zone refining is based on the principle. So see here, they say that impurities which are there, they are more soluble. They are more soluble in their molten state rather than in their solid state. Okay. Because in the solid state you can't dissolve anything. Separation becomes difficult. Okay. So what we do is we melt them. When you melt them, these impurities will get dissolved and separation will be easier. Okay. So that is zone refining principle. You will have to remember this zone refining is also important, and what kind of metals are refined like this, you should know that. So zone refining principle, they say that impurities will be more soluble in their melt state. Melt is molten state. In their liquid state, okay, in the melt state, rather than in their solid state of the metal. So see, using this principle, how it is being purified, you see, they will take that impure rod. You can see here impure rod, germanium is taken here. Okay, and there is a circular heater surrounding them. They will okay, it will be connected like that. Circular heater will be there, and in between this germanium rod will be fed inside. Okay, and this heater at very high temperature it will be. You can see the color. With the color only you will understand that almost it is yellow in color, yellow orange color it is. So this circular heater will be passed through it. When you are passing this circular heater, whatever impure form is there, no, that will start getting dissolved here. Okay, that will melt out. All the impurities will get dissolved here, and as this heater passes by, these impurities also will go along with that. Okay, and it will be collected at the last, maybe at the end it will be collected. It is almost like when you do the cleaning of your house, how you sweep and then you remove all the kacharas at one side, and then your floor will be left clean, no, everything will come at one side. Okay, so like that only even this process works. Okay, so imagine that initially your heater was here, beginning it was here. As you are passing, that impurities will start getting dissolved in that liquid. Okay, and then again you move front, then all that remaining impurities will go front. This will be left free. Okay, so that will be purified there. You're able to understand. At home, if you put water on the floor, whatever mud impurities are there, that will get dissolved into the water, no, and then you will sweep them, you will get them front, so your floor will be left free. Okay, so that's how the cleaning is done. So here see that same phenomenon is applied here for the purification of the metal. Okay, so the circular heater is passed like that. See here, I have taken the actual how they are having the setup, how the setup is. So you can see the melt taken on this side and the circular heater is there. So when you pass that, this melt will like get in the liquid state and all the impurities will get dissolved over there. Okay, and finally it will be collected at the end and it will be broken down. See, the impurities will be removed out and you will get the pure metal. So which kind of elements are purified like this? Which kind of elements are purified? Most of the time it is semiconductors. So high purity semiconductor if you want, like germanium, silicon, boron, gallium, indium, all of these are purified through this method. Okay, is this method understood to everyone? It's a new technique, I know. Refining and all that you have studied before also. Electrolytic refining also you are familiar. But this is something new. If you want, I'll just go back and repeat the same thing once again. So the principle says that impurities are more soluble. So they are in their liquid state easily soluble. So you can heat and remove them out rather than in the solid state. Solid state, it is little difficult. Okay. So what they try to do is they pass that circular heater, heat them at very high temperature. When you heat them at higher temperature, whatever impurities are there, it will go into that melt form. Okay, in the melt form, and continuously when you are rolling that heater, that circular heater which is there, it's mobile, it will move from one place to another place, continuously it will go on like that. So when it goes on continuously like that, these impurities will get dissolved in that. Okay, again you move front, some of the impurities will get dissolved in that, and the left ones will be pure ones. Okay, this side whatever they leave and come, no, that will be purified ones. Okay, and again if you get the heater in front, that impurities will get dissolved. So like that it is continued until last they will bring them. So all the impurities will come at the end, last, like this. Here it will be, imagine that all the impurities has come here. Okay, then it is cut out and removed. Again same thing is repeated, once again they repeat the same thing. When again you repeat, see now imagine once you have cleaned, 100% cleaning will not happen, no. Once again if you put water and start cleaning, you will get little amount of dirt again. Okay, so same thing they have done, they are doing that. So once again they do, imagine that little part again they have got, then this will be cut out, the last end will be cut and removed. Again they repeat. So they keep repeating that till they get that almost 99% pure, no. Till then they keep doing this. I hope now it is understood to you how the principle is, and how they are trying to refine it through this zone refining process. Yes, no, is it followed? Yeah, okay, we'll go for next. Remember which metals, which elements are purified: germanium, silicon, boron, gallium, indium. Most of the time, silicon and germanium question they will ask. They will ask you how high purity germanium and silicon is obtained, which refining process is done. For that, you should know it is zone refining. Don't write something else. Zone refining you will write. Okay, the last, not the last one, the next method, one more method for us is vapor phase refining. Okay, in this method there are two types: Mond's process, because two people have tried it. Mond's process, we are having one arcle. This is also very important. Okay, I'll put a star mark here. This is also very important. Along with the equation they ask, vapor phase refining. So in this kind of refining, you should take that metal which like they will be having impurities. So that metal is made to react with a compound at lower temperature initially, and that when they reacted together, it will give a rise to a complex. First they will form a complex. See, when they form this complex, imagine you are having that metal, it has combined with the reagent, it will form a complex. Okay, and it should be volatile, means it should come in the gaseous phase easily. Vapor phase we are saying, so it should come out in their vapor phase easily. Such a metal you should take. So once they form that complex, whatever impurities are there, that will be left behind, no. Only the metal should combine with your reagent. Okay, so such a reagent only should be taken. So once they form that complex, and most of the time it will be metal which will be forming a complex, so all the impurities will be left behind. Okay, all the impurities will be left behind, it will form a complex. Now you take that complex which is in the vapor phase, again heat them at higher temperature. So this complex will break down and the pure metal will be obtained. Okay, so you will get the metal again, but that will be in the pure form. So this is their whole idea. Okay, hope it is understood. So you should take a metal which is quite volatile, which will easily combine, which will easily react with the reagent and form the complex. And once they have formed the complex, the next condition is it should be break down also. Okay, if they form a complex and stay there like that, then you will not get that metal. So you should take such metal which after the forming the complex also, if you heat them at higher temperature, it should break down easily, it should break down, decompose, and you should be able to recover your metal easily. Okay, so like that we are having two such processes. One is Mond's process and the other one is Van Arkel method. So let's see what is that Mond's process. It is just equation type only. You are not having much. I couldn't get pictures also for this. I tried searching. So Mond's process, see what it is, for which one you should remember. Mond's process is for purification of nickel. Okay, it is for purification of nickel. So nickel is taken and made to react with carbon monoxide, CO. You know, carbon monoxide is a ligand, no? And it's a strong ligand. You know that also. Carbon monoxide is a very strong ligand. So this one here, carbon monoxide is your ligand. Both of them combine together to form a complex. So nickel tetracarbonyl is formed. At a temperature, you see, at a temperature of 330 to 350 Kelvin. 330 to 350 Kelvin. And forming this complex, NiCO4. Nickel tetracarbonyl. Okay, it is nickel tetracarbonyl. It's a common name. If you want IUPAC name, you can write it down. You will be knowing how to write it. It is a neutral complex that you search and write down. I'm not giving that name right now. Okay, so nickel tetracarbonyl. After this carbonyl compound is formed, it's in the complex form. So whatever impurities are there, that will be left behind. And now you are having these in the vapor phase. Now you should take this NiCO4. NiCO4 should be taken. Again heat them because now they should break down. It should break down and recover the metal and remove that carbon monoxide from there. So you should heat them at higher temperature around 450 to 470. You remember these odd numbers. 330 it is 350. And again increase by 100, 450 and 470 odd number. So this breaks down to give you Ni plus the carbon monoxide. 4 carbon monoxide here, 4 here. It's a reverse reaction. Same reaction it is, but in the reverse order. Okay. So it is easy to remember the equation. First equation itself you should reverse and write. Only the temperature has to be changed. Okay. So that's Mond's process for nickel. Another one, this is for this side you write. This is impure nickel. All that you should mention. Even the equations are same, but the concepts should be very clear when you are explaining. That was the impure nickel, and this side what you have got is the pure one. This is your pure nickel. Okay, that is a difference here. Otherwise, equation won't be an issue for you to remember. It will be easy. Let's go for second one now. Second method, again for vapor phase refining itself. Second one is Van Arkel method. This Van Arkel method. This is for purification of zirconium. Which metal is purified is zirconium here. Now see, again same method is same, but the reagent taken is different because zirconium is found to form stable compound with iodine. So zirconium in their impure form is made to react with iodine at a temperature range of around 870 Kelvin. Okay, and it forms zirconium tetraiodide in the gaseous state. So now it will be in the gaseous state. This again you take it, heat them still at very high temperature. See, the temperature is 2075 Kelvin, and tungsten filament is taken so that you get a higher temperature and break them down to zirconium plus iodine. 2 molecule each because 4 has been formed here. So 2 to each. Done. So this is the equation. And mention which state they are in. Here they are in impure state. This is impure zirconium. And this side you are getting the pure zirconium form. This is your pure zirconium. Okay. Yeah, make a note, students. You can remember another metal also along with zirconium. Even titanium is also purified like this itself. But equations you don't have to study for titanium. Only zirconium is given. So zirconium and titanium through Van Arkel method and nickel through Mons process. I hope it is understood. Whatever is done today, different refining techniques. First one I did was, I'm not going back, I'll just revise once. First one, what we did was the distillation that is applicable for low boiling metal, and even liquefaction is also applicable for low melting metals, like we have mercury, lead, and all that. Okay. Tin, they come under low melting ones. So for that, liquefaction and distillation method you have seen. After that, I went for refining technique. Then it was zone refining, refining through electrolytic method, where you have seen for copper. Then zone refining, which I told you for semiconductors it is used. And the last one which I came was for this vapor phase refining. So here condition for vapor phase refining is that the metal, as I told you, the metal should form a volatile compound first, okay, with the particular reagent. After that is over, it should decompose easily so that you can get the metal back. So recovery of the metal should be done. This note also you should, okay, remember what kind of metal and how it should be. They should easily form a volatile compound, then later break down. Okay, I suppose it is understood. So for today, this much would be enough. Okay, I'll continue tomorrow.